Okay, everybody. So before I pass it off to Ashan with McMaster University here, I'm just going to go over some of the CPD stuff. And for the chat, all questions and comment can be sent using the chat feature within the Huba platform. Uh, CPD certificates, like always, will be sent to everybody by the end of next week. Please keep in mind that these are auto-generated using your registration details. So if there is an error in spelling along the way, just reply to your email and we'll make sure to update with any necessary changes. Questions and comments are going to be held, if I'm not mistaken, towards the end. If some impromptu questions come along the way, I'm sure Andy will guide you along. And on that note, I'm going to go ahead and pass it off to Ashan, and we'll start the show.
Great, thank you, Costas. Again, myself, Sean, we joined yesterday. I hope a lot of the same members are joining us today as well. We're going into our second speaker for this event with OSF, which we're very happy to be facilitating. So if you remember this slide from yesterday, I introduced our professional training programs under this new initiative with McMaster University. And I mentioned that Andy, our program lead for the Advanced Technology and Industry 4.0 program to the right, will be joining us today conducting a lecture/workshop with the participants here. I'll be introducing Andy as well, and at the conclusion of the lecture, I'm sure he'll be going into more detail on his 4 courses on the right there. So Industry 4.0, Cyber Physical Systems, Advanced Manufacturing, Hybrid Engineering, Big Data, AI, Cybersecurity, and Automation. So feel free if you have any questions for him, we can entertain that at the end. So on that note, I'll just give a quick overview for Andy himself. Andy started his career as a manufacturing engineer in the injection molding in the automotive sector. He tackled advanced manufacturing at the early stage with Industry 4.0 projects. He translated that experience into a PhD from McMaster University and is now at the University of New Brunswick leading the Advanced Manufacturing Research Lab with that university. He is the founder and principal of IOTM, an industrial IoT company that provides manufacturers with smart industry of Internet of Things solutions. He is also the lead, like I mentioned, with our micro-credential program with the Advanced Manufacturing and Industry 4.0 stream. So on that note, I'm going to stop sharing my screen here. And Andy, I'll hand it over to you.
All right. Thanks for that really nice introduction, Sean. I'm going to just get a hold of my screen here. And I'm sure that if somebody can't see my screen, they'll let me know. Just for everybody's sake, I do have access to Huva on another screen. So if you do have any questions at any point in time, if I can kind of slide the answer in during the presentation, I will. If not, we can hopefully address all of them following the presentation. So again, thanks again, Sean, for that intro. Saves me having to go through that as much as I do like to talk about myself. So let's just get right into it. So I really appreciate this opportunity to talk about something that I'm super passionate about, and this general idea of Industry 4.0. I love manufacturing, and I don't just mean machine tools. I just don't mean steel, any production environment. I find machine tools and automation fascinating. I love the idea of being able to connect devices. Yes, I'm a manufacturing engineer, but I do like to write software as well. So IoT and Industry 4.0 is just super exciting for me. And hopefully I do it some justice tonight talking to everybody. So tonight we're going to talk about Industry 4.0. We're going to talk about deploying with the idea of, resiliency in mind. So I always like to start my presentations with a story. And so in this particular case, I'm going to talk about a common Industry 4.0 pitfall. This happens, in my experience, 85% of the time. So this is a real experience where we had a tier one automotive supplier, had a quality assurance problem, and they were going to apply machine learning to their QA problem. So naturally, they were a very large tier one supplier. The natural thing to do is to reach out to the biggest cloud computing company. Now, I don't want to mention names, but there is one major player in cloud computing, and most of us have a membership to them, and so you can probably figure out who it is. So it's interesting to watch this unfold, and I call it a pitfall because you've got two pieces to the puzzle, or two sides. You've got an OT side and an IT side. So on the OT, that's the operational space. So that's inspection, that's the shop floor. This is the people doing the quality assurance and the quality checks. And on the OT space, they're looking at part defects. They're looking at, in this particular case, they were getting false rejects, or they were getting missed defects. They were looking at things like micro cracks and pitting. And so a lot of their inspection techniques, or the direction they wanted to go with inspection, was visual and ultrasonic testing. And I put in here the cycle time of 6 seconds, and they wanted to reduce it to 2. Then we have the IT space. And on the IT side, it's, what are we going to do here? We're going to collect images, we're going to store the data, we're going to use machine learning, and we're going to automate the entire part acceptance and rejection. It sounds great on paper. Sounds like it should work. After 3 hours, this very rudimentary image is what came out of it. We're going to have a part, we're going to take a picture, there'll be a computer, it goes to a cloud, and there'll be pass fail. That was as detailed as the solution got. 12 people in a room, 7 from the tier 1, myself as a facilitator, and 4 from the cloud provider. So let's talk about the pitfall. I've got up here now a little bit more detail. The OT folks want to differentiate images. They want to look at cracks. They want to look at fingerprints. They want to look at grease smudges. They want 20 photos of a particular part, and they want to analyze the defects. They did not have an understanding of what actually is feasible on the IT space. And the IT folks didn't actually understand the language or what was required in the OT space. It was a shock when they realized that, well, we can't take 20 images, pipe them into the cloud, do machine analysis, and come back with an answer in 2 seconds. There's no way that that is feasible. So I bring this up as a pitfall because it highlights one of the fundamental problems that I see happening in industry, which is there's a language gap. There's a lack of understanding between what IT can provide and what OT requires. So I just put down in here as a couple of extra notes that in the end, there was no faith in the system. And ultimately the outcome was everything got pushed back. And this is a very common outcome of Industry 4.0 projects, so to speak, in my experience. Why is that? Again, it's a lack of understanding, and it's biting off too much. You're trying to tackle a huge problem in one bite rather than taking out just little bits and pieces and kind of chipping away at it. So with that in mind, this is the plan for this evening. I'm going to spend the first half talking about the pillars of Industry 4.0. We'll talk about what those pillars are and the relevancy to industry and really what's driving Industry 4.0. We'll talk about sensors and the really big trend right now, which is edge devices. We'll go into something that a lot of folks find abstract, which is this idea of cyber physical systems, or CPS, and digital twins. And then the last half of it, we're going to focus on actually deploying an Industry 4.0 solution. So I'm going to walk you through an example of just how it can be deployed. And it's actually something that has been deployed, so it's not made up. So I've got some images of the actual sensors themselves and what they're measuring and kind of how we did things. I don't want this to be a deep dive in theory. The theoretical side is not terribly exciting, but the application side is awesome. So hopefully everybody finds this beneficial. So let's talk about the pillars of Industry 4.0 and their drivers. So the 30,000 foot view, which everybody likes to present, is the smart factory. This looks fantastic. It looks like everything's going to be automated. Everything will be connected wirelessly. It gives a really high level view of how the shop floor is going to work, how they're going to communicate with employees. Your supply chain is all managed. Your operations are all managed. HR, field service, R&D, all of these things are happening wirelessly. This image is okay, but this is overwhelming. And this is overwhelming to anybody that's looking at their own facility and trying to figure out, where do I start? A lot of companies, particularly Canadian organizations, are looking at this model, so if you want to call it that, and they're really kind of sitting back trying to figure out where they should go. Hopefully we're going to clear that up a little bit tonight. So here's the big 9 pillars. Advanced manufacturing. So what do we mean by advanced manufacturing? We're talking autonomous systems, robots, lots of integrations, sensors, standard interfaces. And I want to make this clear that when I talk about advanced manufacturing, or I talk about automation, or I talk about horizontal and vertical integration, these are not static terms. Automation for one company is very different than automation for another company. A tier 1 or an OEM's automation level is going to be very different than a shop with 25 people in it. That doesn't make them any less important or more important. So please keep that in the back of your mind. That's another issue that sometimes comes up, where we think that we need to deploy big systems because we're either a really big operation or we're a small operation, and it's not serious enough unless it's a big solution. So advanced manufacturing solutions, additive manufacturing, so obviously 3D printing. You know, the big focus now is metal additive applications. Augmented reality, so AR, VR. We've got simulation, so simulation of value networks. These can be process simulation, operations, systems, supply chains, the whole thing. Horizontal and vertical integration. So cross-company data, integration based on data transfers, fully automated value chains. So vertically throughout your company and horizontally. The industrial internet, what we're talking about there is your machines being networked. Okay, so we already have office networks. We already have an office internet. We're talking about putting this on the shop floor. Cloud storage is a big piece. Cybersecurity is obviously another major element, and the severity of this fluctuates across industries, but it's still something that is going to be, should always be on your mind. And the big one where I think there's a lot of value is this idea of big data and analytics. And so one of the things we're going to do today is I'm going to show you a couple of sensors. I'm going to show you the data visually, and how we can do a couple of little tricks to manipulate that data to get some value out of it. So academia likes to talk about pillars. I prefer the word drivers. What are the things that are pushing Industry 4.0? And while, you know, this is very similar to the pillars, the ones that I want to focus on today, because as far as I'm concerned, these are the drivers, are sensors, digital twinning, and edge analytics. When you think about Industry 4.0, Industry 4.0 isn't blossoming because of cloud computing. Industry 4.0 is not blossoming because of machine learning algorithms. They all rely on data, and data comes from somewhere. It comes from sensors. It is the fact that the sensors are cheap and they're readily available, although there's been a few disruptions as of late for the obvious reasons, but sensors are cheap, and getting that data is very cost effective now. That is why Industry 4.0 is taking off. It's become affordable. And you don't need a PhD in order to do it. So when we talk about the initial drivers, again, we're talking about sensors. And as we walk through to an Industry 4.0 and a digital twin and a cyber physical system, we're really talking about this idea of a sensor having some level of connectivity, edge analytics, and a digital twin. All right, there we go. So let's talk about sensors and what they actually are. And I'm sure lots of people already have some foundation in this, or they're familiar. Well, first of all, you're all familiar with it because everybody, I'm sure, has got a cell phone. And your cell phone's only got about 15 to 20 sensors built into it. So a basic sensor overview. There's obviously digital and analog. We get into environmental monitoring, image analysis. I'll call it dynamics, so motion and vibration, prox sensors, and how they do that can vary from one sensor to the other. The sensor design, so the big thing right now is embedded systems. So that is a PCB, that's a custom built board with the sensors embedded into them. Your phone is an example of that. You can have standalone devices, which is what you'll see in a lot of academic institutions and industrial applications. You may have a standalone device. You will see that in industrial applications, and that is becoming much more common with the real advent of edge analytics. But at the end of the day, they've all got the same requirements. They all require power, and they all require usually some type of digital analog conversion, some type of data acquisition system behind them to get the data, connect it to a database, store the data. So all of the requirements, they're still there. So whether you've got a standalone device, a wireless that's wired or wireless or embedded, they've still got a lot of the fundamentally the same requirements. So here's a couple of examples just of, one on the top right is a couple of basic force sensors. Right below that is a series of current sensors or power sensors. Those power sensors down there probably $10 each. So when you're thinking about what sensors am I going to use, or what sensors should I be using for my IoT system, and I think you're probably recognizing I'm going to build this from the ground up. We talk about suitability, reliability, accuracy versus precision. Are they industrialized? Most of the stuff that you will see in an academic situation is not industrialized. What kind of calibration do you require? So from a QA perspective, you need to know if they're calibrated. Do they need regular calibration? Do they drift? Depending upon what you're monitoring, what type of signal conditioning do you need to do? So as an example, if you're monitoring power and it's in the controller and it's in a big metal box, that can be, as simple as it sounds, it can be a challenge, simply because it's a very noisy environment. So while you're trying to maybe measure power, maybe trying to pick up information can be a challenge. So these are all things that have to be considered when you're looking at what kind of sensors do you want to deploy. This, of course, assumes that you know what you're trying to measure. Is any one type of sensor better than the other? So the two sensors I've got up there measure the same thing. One is $600 US and one is probably, $80 US. They will both do the same thing. Is one better than the other? Well, it depends on what exactly you're trying to not so much measure, but do with that data. So there's lots of different ways to connect equipment. And everybody's going to need their own plan of action. So understanding what it is that you want to measure, knowing how you want to connect that up. It's not a one size fits all. So even the small little power sensors that are in that image, they are all unique in the sense that it's not a one size fits all. If I've got 10 amps, 20 amps, 30 amps, 5 amps, they all require different sensors. One of the things I always stress with Industry 4.0 is you cannot forget about people. Okay, so you really need to think about what is the data that people need? What are the goals that those people have? What type of information do they really need to be getting? So even the bits and pieces of information that you're trying to capture and how you want to communicate that, you need to keep people in the loop, because in the end, while I'd like to say we're all going into AI and machine learning, we've got a long ways to go before we're going to start giving up control. So it's really important that we think about people and the data that they require and how best to communicate that for them to make decisions. I've got here the sensors, they're cheap, relatively cheap. and they're almost to the point where they're plug and play. Some of them are plug and play. If you buy something from the same vendor, they will be plug and play. You get wireless sensors or overlay solutions attached to existing machines, are super cost effective. They use a common set of technologies. The one thing I warn people about is be careful when people talk about open systems. Not everybody talks to each other the same way, so sometimes that can be a bit of a roadblock, but it's still easy enough to overcome. So you have a sensor and it's sensing something. They obviously will connect to microcontrollers. So microcontrollers are a really nice, slick little way of powering a sensor and reading data. So if you've got kids that are into technology, particularly on the tech side of computing and embedded systems, that you may have heard of Raspberry Pis, Arduinos, BeagleBone Blacks. You can literally buy a board now that's half the size of your hand, and it's a full-on computer, and you can actually do AI on them now. That's how far they've advanced. So the sensing side and the data acquisition side is just racing forward. The old standbys in industry are still there, obviously, particularly the PLC. The PLC isn't going anywhere. The PLC is the heavyweight of the microcontroller. They're rugged, they're industrialized. One of the nice things that I'm seeing out of PLCs is that they are starting to have a lot of versatility. So one of the beauties of having a small microcontrol unit is you've always been able to have a lot of customization, and everything was open. PLCs are now moving in that direction as well. And that's a great step forward for PLCs. That being said, a Siemens PLC wants to talk to Siemens hardware. They'll talk to any sensor, but when it comes to HMIs and human machine interfaces and communication, we've still got some hurdles there in terms of getting everybody to play nicely in the sandbox, but we're getting there. So I'm telling you that sensors are driving everything. They're still the weakest link. They are getting better, and that's why I wanted to talk about edge analytics tonight. There are some concerns about what they can and can't do, particularly the compatibility especially in noisy, adverse manufacturing or environments, and they're compounded by real-world constraints. So going online and finding a sensor, it's sometimes not that simple, depending upon what you're going after. Short time constants. So being able, if you got something that's fluctuating very quickly, you need to really think about what you're getting there and what you're looking for. If something's got a lot of localized changes or really large gradients, so in other words, huge swings in data and values, that might be a challenge, especially sometimes if it's over several hours or it's over microseconds. You need to think about all of these things. Chemical change monitoring, anything with fluids, a lot of this stuff is highly nonlinear. What do I mean by that? I mean that you just don't simply, if you scale one thing by a factor of 5, you don't scale a sensor by a factor of 5. So, you need some understanding there. Point measurements, excuse me, a lot of sensors are still using point measurements. That can be a challenge with 3D shapes. One area that's gaining some traction in some of the work that I'm doing is this idea of inferred measurements. It's interesting because there's some things that you just can't measure directly. So understanding what types of technology and sensors you can use and kind of concatenate that together to tackle the problem that you specifically want to address. All right. So when we talk about sensors in Industry 4, what are some questions we need to be asking? What are you trying to achieve? Is it just data collection? Maybe some analytics? What are the variables or parameters that you are trying to get information on? How are you going to communicate? What are the best or most suitable sensors and the accompanying acquisition system? So obviously a sensor by itself isn't that useful. You need something that gives it the power and does the acquisition. And then what are you going to do with that data? Where are you going to send it? How is it going to be managed? And of course, the big one, if you really want to go to get to the smart factory, is how scalable is this? Where are we going with the future expansion? So what I always tell people is transform your machine, your work cell, or your factory floor one sensor at a time. You don't require, nobody needs to require massive investment in brand new machine tools. Smart manufacturing technology can be adapted to existing equipment. Attaching sensors to legacy equipment is often really simple to implement and then integrate into your own systems. Yes, you can collect data off a manual mill or a manual lathe. It can be done. So don't feel like in making that transition to Industry 4.0, we need to junk it and get new equipment in there. That's definitely not a necessary element to get to even a smart factory. The big one I highlight here is how is this implementation going to be communicated to people? When we ran one of these sessions with some aerospace folks, and I did some design thinking exercises that IBM facilitated. I don't know why I hadn't thought about it, but one of the number one barriers with adoption was the stress level. The stress level that people feel when they see an integration company walking out into the office or into the shop floor. So how is this implementation going to be communicated to people, and how are they going to be married up with this technology? This is really, really critical to the success of an Industry 4.0 project. I don't care how good the sensors are and your data acquisition system is. If you do not have buy-in, you will not succeed with your Industry 4.0 project. So we're going to talk about tech, but it still revolves around people. Really quickly, couple of things that five things that we should be thinking about with sensors. So the 5 V's that we call them. So depending upon what it is, you need to deal with volume. So if it's an image versus a point, that's a very different amount of volume. If you've got a variety of information coming in, how are you going to manage that and store that? So Facebook is an example where you've got a variety of data coming in all at once. But you could imagine in a manufacturing operation, reading an RFID tag, getting a force measurement, getting a power measurement, and getting something visual all together. And how do you manage communicating that information and making semblance of it? Value. This doesn't get talked about enough. When I think about value, I think about what we call the hidden factory. 90% of the data floating around there is what we would, in manufacturing, is what we would call dark data, i.e. it's just out there and nobody really knows it's there or knows what to do with it. You don't believe me that it's that big a volume? Look at your own laptop and see how many spreadsheets you have of the same information, or the same information just slightly tweaked. I'm super guilty for that. That is considered dark data. It's important to recognize that it exists because A, there could be value to it. So can we pull value from it? And number two, equally important, is a lot of times dark data goes unprotected. So from a cyber standpoint, we want to make sure that all of our data is locked up tight. Veracity basically deals with this idea of inconsistencies and uncertainty. So making sure that your data is reliable. This is really important. Again, this has a dramatic impact on whether or not you're going to get any type of serious buy-in. Really quickly, sort of the latest trends. Smart sensors are the latest trend. And by smart sensors, we're talking edge analytics. So we're talking about a sensor integrated into a board. The data acquisition is happening on the board and the analysis is happening on the board. So it's not about remote anymore. We're still dealing with miniaturization. Sensor fusion is a big one. So we want to have systems where we can have one board with lots of sensors on it, doing lots of analysis very, very quickly and doing the correlation. You've seen an explosion in IoT devices. Wired systems are becoming cumbersome, and they're not and too complex when it start getting into high volume data traffic. So you're starting to see a lot of wireless sensors become the norm. Those architectures are going to be unique. Obviously, data management's a big one. So the challenge is, how are you going to manage all this data that's being generated? How are you going to standardize that data? Are you going to standardize that data? You know, there's no rule that says you have to use a standard SQL database, which is a very structured database. You can now go to a non-SQL, and you can couple all kinds of different data together. That's a really high-level topic. That's a big topic, and not one that you need to worry about if you're just getting started out. But it's nice to know that that is out there when you want to start taking maybe a small project and scaling it up to something bigger, or marrying it up to another Industry 4.0 project. And obviously the integration of sensors into products to improve quality. This is something that's coming. I haven't seen any of that in practice yet in terms of my own manufacturing experience, but I have heard about it in terms of particularly packaging industry getting more into this type of technology. I've got 2 slides on edge analytics, and I think that these are super important because what you're starting to see, so really quickly, edge analytics is this idea of having all of these sensors. So I've highlighted device and sensor. And rather than, you know, in our example, we were going to send everything out to the cloud and try to do the analysis. Well, we don't need to do that anymore. We can have, say, on a specific machine tool, we can have everything located locally at the machine tool. If, say, we were tackling machine maintenance, we could have a force sensor and some power sensors or something monitoring a pump, and we are going to be able to put that all together and very quickly make decisions on machine tool performance or quality. Now, one of the questions I saw come up here was, can you give an example of an industrial IoT device that uses wireless sensor applications? I'm actually the timing, so that's from Bob. Bob, the timing's perfect to ask that question, because that is actually what's going on now. So, and I'll give you an actual example because I had a meeting last week with a company that does valves. So inside of their valves, they're actually embedding flow control. So they're embedding temperature and flow sensors. On the valve, they've got a board that is actually doing some analysis as to what's going on. And then there's a wireless chip through Bluetooth that's communicating to a central location exactly what's going on. So a lot of the IoT device, when I say wireless, a lot of it is moving to Bluetooth. And there's actually, if you start looking at flow control and power sensors, I'm trying not to use names of companies, but it is coming up now where you can get actual wireless IoT devices for data collection. I like the idea of the wireless data collection. The part I struggle with, to be quite honest with you, is ultimately I see value in getting that information, doing the edge analytics, and then, yes, it's important to communicate data, but a lot of industries looking to go to the next step and get some immediate feedback, some immediate control. So in order to have that, I'm not as excited about the wireless technology, simply because there's a lag. Whereas the connected hardwired devices are able to collect, analyze, decide, invoke a control command. But that being said, you are seeing a lot of wireless devices, particularly in environmental monitoring. So you're seeing this in aquaponics. You're seeing this in deployment in aquaculture, and they're all using Bluetooth and radio frequencies, so radio communications to connect data. Agriculture, surprisingly, is a good place to take a look at how they're using wireless sensor applications. I don't know if I answered your question. I'm trying to be very roundabout as I tackle this. The real benefit with the edge analytics here, though, is quick decisions. They're affordable, and they can give you a very fast digital transformation. The other advantage is they do create opportunities. They allow you to do some on-site or local data mining, and they allow you to test out refined algorithms. So what do I mean by that? We have work cells. So a work cell might be 3 or 4 machines. They're all connected up into a cell. That cell is connected up maybe into a line. That line is connected up into a plant or a factory. That plant is connected up into a series of operations or supply chain. But if you think about the idea that you can now test out different algorithms and you can test them out at different levels, that can actually be programmed right on the actual embedded system. So the edge analytics are really taking off. The reason I'm spending time on it is this is where sensors are going to go. Doesn't mean we're not going to still have wired in or wireless sensors as standalones. However, you're starting to see edge analytics come in where they're using a wireless IIoT device embedded on a chip. The wireless is only used to communicate the data out, but that edge device is still wired to the sensors enough that it can invoke some controls. We're not doing a lot of wireless control in the manufacturing environment unless it's long lead times, simply because, again, you can't have machine tools or heavy pieces of equipment suddenly making adjustments and not communicating that properly. It's just not a safe environment yet. So creating a CPS or a digital twin. So in order to do this, it's about taking the abstracting and making it practical, or the practical and making it abstract. So this is a nice image here, and I like it because on the left-hand side, you've got a CPS, which is a cyber physical system. I highlight physical system. It is a real thing. So on the left-hand side, and the only thing we're really focusing on tonight is the bottom left 3 triangles. Pieces of equipment, that's a cyber physical system. That could be a machine. A component could be a piece of tooling or a consumable. That is a cyber physical system. A piece of material that you're tracking through the facility, that is a cyber physical system. As you elevate that, you can get into scaling them up so that you get production lines and smart factories. And then ultimately we get into this idea of a smart service platform. On the right-hand side is the digital twin. So this is the side that's communicating digital information to the user. And this is obviously extremely important as well. So you've got a material digital twin, which could be nothing more than a piece of data on a screen. Same thing goes for the components. A piece of equipment could be a schematic of a piece of equipment with a bunch of numbers floating over it, just telling you how the machine is operating. So the digital twin is actually this virtual twin or virtual machine or virtual device that we're communicating to a human. The cyber physical is actually the physical system wired in with the appropriate technology to create the digital twin. So again, what's the difference? It's a cyber physical system. It's the core of Industry 4.0. If you want to start thinking about the pillars, it really is, you don't have a digital twin without the CPS. You cannot have a digital twin if you do not have sensors in your machine tool. That's just the way it is. or some form of data that's communicating information about your machine tool. Too often we think of digital twins as this fancy 3D model, like a video game running in tandem. It can be that, but it certainly doesn't have to be that complicated. So here's an example. There's a machine tool. It's actually not a machine tool, it's an oven. And they have 3 or 4 things that they're monitoring. And they've got a really nice display in the sense that everything is graphical, and they use words like normal, stuck, so everything's very quick so that decisions can be made very, very quickly. And this idea of being able to click on different elements, I'm assuming you can see my mouse kind of move across, but you can click on different elements to get different pieces of information. And of course, the future direction then is we take the shop floor, this physical system, we wire it up with sensors so that we create all of this data, which is done to create all of these models, which allows us to create a virtual platform that feeds back into our shop floor. Again, you'll see this deployed on an Amazon shop floor, but they're only moving product. And I should say they're only moving product. They're moving product. You'll see this in storage units where they're able to do this. We're not talking about having 100 machine tools collecting, gigabytes of information every few seconds. All right, so let's talk about what really excites me is how could we actually create a cyber physical system and ultimately a digital twin on a machine tool. So I'm going to focus on a specific machine and a specific process. So I revisit this image. But as Sean mentioned, I'm a manufacturing engineer. I really like the smell of cutting fluid and oil, and just the sound of machines. I'm like a little kid when I get in there. I'm fascinated at what we can do with machine tools. So I'm going to use this as an example. It's a 3-axis milling machine. If it's 5-axis, it doesn't matter. It's the same technology. And I'm going to choose a drilling operation. The example I'm going to use, we'll talk about it at the very end. I'm going to use drilling because drilling is the bulk of our machining operations. It's the oldest technology, and it's still being used, and it constitutes a high amount of the machining work that we do today. So the example there is we've just got a simple twist drill going into an aluminum engine block. So when we're trying to decide what is our cyber physical system going to look like, how do we figure out what the hell we're going to do? What are we going to actually integrate into our machine tool? I'm going to go back for a second. You'll notice here there's a controller on the machine tool. They are typically closed. They are typically a black box. Yes, you can get some information from them, but if you're really looking to do AI and machine learning and get into some analytics, I shouldn't use AI and machine learning. They're big words. If you just want to do some analysis, it's really hard to do with these controllers. They are still black boxes. So we're going to go in and we're going to create our own CPS. So what does a machine tool do? That's really simple. It removes material using some form of a cutting tool, whether it's a drill, whether it's a single point turning tool, whether it's an end mill, broaching tool, a grinding wheel. They remove material. So when you want to map out a CPS on a machine tool, the first thing is to recognize what are your inputs to a machine tool. Now, I don't want you to be thinking about G codes and CAD information and CAM information to program the machine to make it go from XY to XYZ and ABC. I don't want you to be thinking that way. I really want to drive down into what does a machine tool need to work? It needs power. That is what it takes. It takes electrical power and does something. So when I think about inputs, I think power. I have a controller that pulls power. I have a spindle that pulls power. I have feed drives that pull power. Spindles and feed drives, they're motors. I have all kinds of auxiliary equipment that pulls power. So you usually have an air system in your machine tool. You've got pneumatics in there. You've got a lot of sensors that are built into the machine tool as safeguards. So a machine knows where its 0, is or how to home itself because there's sensors in there that tell it where it is. Machine tools are not smart. They do what we tell them. Tool changer. You're certainly going to have power that's got to be tied into that. A coolant pump. All of these different things need power. So I think we're pretty clear on our input. What are the things that we can get out? Well, if you want to start removing material, you're going to have forces. You're going to have sound. You might have temperature. Maybe there's some vision cues. In certain applications, maybe using cameras to do thermal analysis or something like that. You're going to get positional information, and by positional, I mean geometric information. You get speed and duplicate geometry. Well, let's be honest. You can get power from your controller, your spindle, your feed drives, auxiliary equipment. Well, certainly your controller, your spindle, and your feed drives, you can get that from your controller, and you can get position, speed, and geometry from your controller in a machine tool immediately. You cannot get force, you cannot get sound, you cannot do vision, you cannot do temperature, and you are not going to get any information about your pump or your tool changer or auxiliary equipment. Other than you might have to do a little bit of math on your own. So that's fine. So let's look at these two, the left and the right, and let's think about our inputs and our outputs again. I can measure power anywhere in a machine tool. That is very easy to do. I showed you a bunch of little blue sensors. And guess what? I can measure force, and I can measure sound, and I can measure temperature, and I can measure geometry. And these are all independent industrial IoT devices that you can deploy very quickly on your machine. Now, if you're going to go with an embedded system, it's a little bit more cumbersome, but you can certainly deploy them as individual IoT devices. So when I look at this, we're going to break it down a little further. Power is AC/DC. It's a bit of a pain because it's three-phase. A lot of it's three-phase. Where are you going to monitor that? Do you need to calibrate things? Is there signal conditioning issues, sampling rates? Forces could be in 2D, they could be 3D, they could be torques. Again, the idea of calibration, signal conditioning, sampling rates. Sound I put up there. Sound is a tough one. It's directional. You got to think about filtering, its frequency content, signal conditioning. So we're not going to put that in here. But understanding your process and the physics of your process and your operations on a bare bones electrical, mechanical, material, and compute principles, if you know those, then you'll have a better idea of where to deploy IoT. So first of all, I'm telling you right now, what I'm going to show you is we're going to monitor power and we're going to monitor forces. And I'm going to show you how we do that. So we're going to go after this drilling process. So there's an example of a good drilling process and a bunch of bad drilling processes. Now, you're going to get variability in your drilling process depending upon the types of drills, the parameters that you're using, the material that you're working with, the tool quality, and you're going to get different variations of this. But at the end of the day, most places that are drilling holes, there's always QA afterwards, and there's a lot of deburr and cleanup. Drilling seems simple. It's extremely difficult. It's a rotary tool. It's super complex. Everything's moving. Controllers display what the machine tool is doing. They do that for the operator. You may or may not be drilling with coolant. So there's a lot of different things that go into particularly drilling operations. And in this case, I'm showing through hole drilling. So power. Here's a couple of cheap sensors. With force, okay, these transitions aren't going the way I planned. There we go. So with power, I've got two examples. In the top left, the $600 sensor, that is a three-phase power sensor. It is an embedded system. It monitors current, it monitors voltage, it does the math immediately for you, compensates for any lag between current and voltage, and spits out a power value. Really nice. The ones on the lower right, under power, they're the cheaper ones. They spit out current. That's all they do. And they rely on the little board that they're plugged in to monitor voltage, and then you program your system to do a power calculation, which is, voltage times current. Force transducers. This is a very expensive setup, but you can get those very cheap as well. So this is for a large scale setup, so that's an expensive table, but you can get devices that look similar to the sound sensors to the right, and you can get those for $25, $40, $50 each, and you can wire those in. So we're going from these sensors, and I told you we're going to focus on power and force. So I pulled open the controller on my machine, and there's the mess that I call my machine tool, the control cabinet. But I've got two embedded systems in there. Now I went with the expensive ones. So here is one in the top right. This is a three-phase power sensor, and all I'm doing is I'm monitoring the power coming directly into the entire machine. And then I have another sensor to your right, and that's monitoring the power on my spindle. So I've got two sensors that are monitoring my spindle drive and my total consumption of my machine tool. On the force side, I've deployed a table dynamometer, and again, they are expensive, but I could have gone with a regular flat tombstone, similar to the one that's already on there on the table, and I could have mounted standard force transducers underneath that, and I could have done the exact same thing. If you're wondering why the hell did Andy go with the expensive ones, it's because I wanted to do some control. So I needed the accuracy and the reliability and the ability to talk to the machine. So what do we get out of them? By the way, these guys are just wired into a computer. They're wired into a data acquisition board that takes the data and sticks it into a database. We monitor the data using Excel. Schools like to use MATLAB, but you can use Excel. So here's a set of signals. One is from the forces, top right. So this is what the force signal looks like when I'm drilling a hole, a through hole. So that is the force that is generated axially as the drill tries to push through the material. The lower left, this is the power that's being consumed by the different drives in the machine tool as you're drilling a hole. You'll notice they kind of look similar. Some of the values are different, and it makes sense that they look similar. Obviously, as the forces go up, you have a larger draw on your system, and as the tool breaks through the material, forces and power are going to drop. So this makes sense. You're looking at this and you're thinking, well, there's really not a lot that I'm going to be able to discern from this. Well, okay, well, let's look at a few more things. Let's pull in some other data that we're getting. So this is just an example of us drilling multiple holes, faster and faster and faster on the left, and monitoring power signals. Looks pretty rough. At the same time, you might be looking at this saying, okay, well, again, I'm not seeing what's going on here. This is just data. So this creates a nice signal. You can smooth it out if you want. A lot of times this is just noise, and you can do that, particularly as the tool is breaking out. And we're going to get into a little bit of math. And when I say a little bit of math, we're not talking complex math. We're talking about mapping these curves out and doing something like taking a derivative. So in this particular case, we were looking at the difference from point to point to kind of get these nice smooth curves. So the data on the lower left, the data on the left-hand side, and the data on the right-hand side are all the same. All we did was we looked at the data in a slightly different way. So we took a sort of a differential approach to the graphs to the right. So when we look at this, we say, oh, well, looks like something's happening. Obviously, the difference flattens out when we are not drawing power anymore. So, we've got a rate increase and then things kind of taper off. So we know that this is a good representative of the drilling process. However, this curve is nice and smooth. So I put all of these together and I come out with a curve that looks like this. All we did here was take the second derivative of the curves. And a lot of times it's that simple. It's taking raw data, graphing it out, coming up with an equation, taking a derivative of it, maybe integrating that data, maybe integrating it a second time, and looking for patterns. Now you're looking at this, so you'll notice here we've got things kind of are very steep, and then the slope drops to 0. Now I'm looking here and I've got these two little bumps, and they're consistent. The question is, could this be considered the signature of a good process? That is exactly where we're going with this. Thank you for asking that. So I'm circling that point. This, now I know that this is true because we ended up taking this signal and matching it up with physical through-hole / burr drill specimens. But this indicates that a burr is going to form. Not only does it indicate a burr is going to form, this image actually tells me when it's going to form and how big it's going to be. So the reality is, when we talk about the signature of a good process, let's suppose that this particular one that I've got with the circle around it is the ideal case. We could compare that to figures A, B, and D to find deviations from a good process. I love that question because in the end, edge devices and deploying sensors in a really simple scenario allows you to actually characterize your machines. It allows you to characterize your equipment. If you've got a sound process that you're happy with, you can come out with that signature process. And then what you're doing is you're looking for variability and deviation from that. And if you get really good, when you see deviation, you can start to tie that to physical actual issues in your process. So and maybe relate those back to quality issues. Maybe it's a maintenance issue, maybe it's a tool wear issue. Let's be honest, if I start using a dull drill, so all of this work, by the way, and I would have forgotten to mention this if that question hadn't been asked about a signature process, was done with a sharp drill. The minute you start to have a dull drill, this curve is going to become, these bumps will start to become more pronounced. And so this one here is slightly more pronounced, and you'll start to see more variability. My scales are all a little different here, so it's not a fair comparison, but I really love that question. So yes, this is how you can develop a characteristic or signature process and then look for deviation. And I want to back up again. I wanted to remind you, it was a force sensor and 2 power sensors. This that I'm showing is an expensive solution because I'm an academic and I'm a great spender of other people's money. When I'm deploying my own solutions, it's $1,000 solution. It's a $1,500 solution. Maybe it's a $3,000 solution. But when you start saying, hey, for $3,000, we're going to develop a signature process, that's tremendous value. And the return on that investment can be really quick, especially if you've got a lot of variability in your process to begin with. So we focused on a problem here of reducing and eliminating burrs, but at the end of the day, really what we're trying to do there is we're trying to look at what type of technology should we be deploying, and that's based on what are our inputs, what are the things that we can measure, and then also what are our outputs, what are the things that we can readily measure, and how quickly can we measure those, how reliably can we measure those. So in this case, we focused on a problem of, we wanted to understand from a purely theoretical standpoint, what is the link between measuring three-phase power in different points in a machine and being able to identify a deviation from an ideal process to predict, in this case, burrs and drilling. Well, now we can go all kinds of directions. We can look at what type of burrs are forming, how do they form. Maybe some burrs are acceptable. So maybe we can start to find, we start to define bands of what is acceptable in terms of your process variability. Can you make adjustments on your machine? Maybe we extend this into a control scenario, so we start changing machine parameters sort of on the fly. We can do proper analysis with new tools. I've seen it before where people will adopt new tooling and find that they end up deviating from their ideal process even further, or in the long term, they're not getting the return on the investment. So this is a really quick way to start to roll out an IoT solution. You'll notice it's very focused. It's not about, hey, I'm going to develop a smart factory. It's about biting off one little piece and going forward with that and seeing it to its end. What else can you do with power? So I mentioned we tackle burrs. There's no doubt you could tackle quality from this. You could tackle machine tool maintenance. You could tackle process efficiency and identify weak areas and improve on them. Tool wear, energy management. Nobody understands their energy bill. This is a great way to start to get a handle on that. You can get into optimization and prediction for all of those elements. Imagine being able to come up with, from a costing standpoint, not only when you make a part for me, can you tell me how much time it takes, but you can tell me the energy footprint of that part. And then when I tell you, well, I want to make a change and I want to make a new part, and this new part's even more green, since that's the buzz right now, you can actually do the predictive analysis to tell me, no, it's not. It's much more labor intensive. It's much more energy intensive. Or, yeah, you're right. This is a much slicker design. We're going to be able to manufacture this quicker, higher quality, and it's a smaller footprint. This type of technology really improves your adaptability. It can make you more agile. Of course, it depends on the data you want to use, but by having that sort of grassroots knowledge of your process and what's going on with just some simple IoT and edge devices, it really, really helps you to be able to pivot when you need to head problems off before they come. And while I know that we talk a lot about lean in manufacturing, agile is something that's operating in parallel now, and you're going to need both of those. I like to talk about people really quick. The old adage, don't bring me problems, bring me solutions, forget it. I know a lot of us were taught that in school. Unfortunately, I work in academia. I have one foot in academia, and that is still a prevalent thought. I'm fortunate enough that I only teach graduating students now, so I do my best to untrain them of starting with the solution. The trend now is experiential learning, so that's really helping to address this. I think, and this is not catering to the audience in any way, the colleges are miles ahead of the universities right now in terms of providing the experiential learning to new grads, which is really going to benefit people. When people are coming into your facility, you need them, off and running as quickly as possible. OT and IT, they've already got their methods that focus on identifying problems and continuous improvement. So, really trying to find a happy medium between the two of them. We don't operate in silos anymore. That is not going to work. Operations and production guys like to use Kaizen bursts. IT and technology, they like to use sprints. We're going to need to find a happy medium, and that long hallway that existed for me between my desk and engineering, so that I had time to calm down from my coming off the shop floor to engineering. That long hallway can't exist anymore between the departments. It's an all hands on deck. Whatever solution you come up with, it's going to impact people. So be aware of that. Make sure that you're communicating it properly. It's just so important. Even the drilling example that I've walked you through, somebody seeing that without understanding why you're doing it, it can be threatening, and you need to be empathetic to that and address it. So hybrid teams are a really good way of getting around this. And by hybrid, I mean lots of different folks, different backgrounds, different levels in the company being involved. Break down barriers. Some cases, the ROI is not good. The power sensor ones that I'm showing you, the ROI is excellent on those. There'll be other much larger systems where the ROI may not be there, or it may be extremely difficult to quantify. You're going to have to accept that as you move forward. So focus on the pillars, connect them to participants and their experiences. Design thinking exercises are always a good way to go. Think about the business case and keep people in the equation. I'm going to talk for 2 minutes just about how we're addressing the skills gap, since it is McMaster here. I'm not going to get into a big sales pitch, but I want to talk about what we're doing. So this is a repeat that we are focusing on the Industry 4.0 pillars and connecting participants to experiences. So the example that I just kind of very quickly walked you through, we're going through that in detail. So we're talking about actually having the machine tool running, and it's probably going to be streaming, but the machine tool running, live video feeds of the sensors, live video feed of the data acquisition, and talking about different ways to communicate things. We're talking about having design thinking exercises where everybody's participating and talking about what are the barriers that exist to developing a good understanding and adopting these technologies in your own facilities. How do we make the business case, and how do we keep people in the equation? We do a lot of case studies, and we have a lot of guest speakers. So case studies are important. Most people that jump into these things, I don't think they need to be sold on the value of IoT, since a lot of people are moving into it. I think that this is a critical piece where you can kind of see some of the overlap with your own facilities. These ones here are particularly geared to aerospace, but we have case studies across the board. And it's good to always see what they're doing. We do connect the challenge with experienced solution providers. And I want to stress here that we don't, these are not people selling their products. These are not people selling their solutions. These are people that really believe in the Industry 4.0 paradigm. And they want you to adopt it. Hey, let's be honest. If you get heavy into an IoT solution across your shop floor, you're probably going to be dealing with IBM or Cisco or maybe ATS or somebody like that. But the nice thing is these folks have worked with us extensively. They understand what our participants are looking for, what my expectations are, and they're really good at just getting everybody moving in the right direction and trying to knock down some of those barriers. Just a list of some of our guest speakers. I'm going to make this presentation available to everybody, so I don't think we need to go through it, other than highlighting that, the bank, aerospace, robotics, simulation companies, integration companies, compute companies, associations, we're working with all of them to create a really unique learning and networking environment for everybody. So really quickly, this is me again. I don't think I need to reintroduce myself. My contact details are here. Just highlights my passion. And that's what I look like. That's all of me. And like I said, my email is here. My phone number is here. You can reach out to me at any time. I'm always happy to talk shop. And if you've got questions, I'll do my best to answer them. Thank you very much. So I think what I'll do is I guess I should stop sharing my screen maybe. Costas, I'm not sure how you want to, what's our next step here? I probably should have confirmed with you first.
Yeah, no worries. I mean, thank you for the presentation. You can leave it on here so people can see your information, or we can take it off. That
No. I'm going to put it back up then.
Yeah, and then if there's any questions, again, everybody, now is the time. Now is the time for you to ask them. Yeah, and then.
So yeah, I'm just as I know I've answered a couple of these. So CPS risks and how to manage them. Good question. So in a couple of deployments that so I'll give you an example actually. I did a deployment and it was one of the very first times I'd ever done one. I didn't do an awesome job. I know I'm not selling myself very well now. What do you do when the power goes out? So what are risks? If it's critical data, how are you going to mitigate risk? So how are you going to manage issues like a power outage? How are you going to manage a loss of communication? Those are real risks. How are you going to manage somebody tampering with it? So we get into the cyber element of it. Some of the physical pieces in terms of power, what if we lose communication? Those can be mitigated through edge devices. So a lot of times what I'm trying to do a lot more now is rather than having continuous direct communication from my sensor to my data acquisition system to the cloud or some other server space, we're using the power of the edge device at the machine tool to store it and push it across in blocks. The only time that gets really, really messy is if you want to get into control. And when you're getting into control, now you're talking about having very fast turnaround in terms of analysis and tweaking your machine tool. We're not there yet. Some machine tools are getting there, but we're not there yet on a mass scale. What's the current maturity of Industry 4.0 in Canada? Those people that know me, I mean, Sean's been around me enough that I tend to be really direct, probably too direct for my own good sometimes. It's not good. So that's I guess that's not a fair statement. There I am being too direct. It's certainly not where it should be. A lot of companies are in the wait and see mode. There are a lot of companies that are in that mode simply because they're overwhelmed by it and they don't know where to start. The Canadian government is no farther ahead either. So this is something I'm seeing across the board. The US is farther ahead. Europe is certainly much farther ahead, and we've got a long ways to go to catch up to Asia in terms of deploying technology and using it. That being said, we have unbelievable manufacturing, what I'll call tribal knowledge here. And we need to be capturing that. And so while we're not where we should be, we're pretty good at part tracking. That's about as far as we've gotten so far. We're good at tracking people's hours. There's lots that we can do. And there's lots of little things that we can do. I wish we were farther along. I'm not going to put a number on it, but we aren't where we need to be. On the topic of outages and comm failures, I think this needs to be an upfront discussion, decide if, excellent point. So this gets back to your data and the value of your data. I mean, I didn't really spend any time talking about the types of data and the value, and whether or not it's sensitive. If you're operating in the aerospace industry, that's much different than operating down the street in a small forming shop in terms of criticality of data. So you're right, Joseph. There has to be an upfront conversation on what type of data, and that's kind of what I was alluding to, and maybe I didn't do a great job of it. You need to have that upfront conversation. What type of data do we need to be getting? Is it relevant? Because if it's not, let's not get it. Let's not go after it. But if it is relevant, how critical is it to our operations? I 100% agree. That has to happen up front. And that's, I think, to your point, why you need to have multiple people in the room. This can't be a conversation between the production manager and the general manager and the director of IT. That cannot be the only people in the room having that conversation. There needs to be multiple people in the conversation, multiple stakeholders, because you need to understand the value of that data, both vertically and horizontally in your organization. And yeah, it does impact the cost and complexity, for sure. Now I'm looking at the Whova app when I'm looking for questions. I don't know, I haven't been monitoring the app in Zoom, but I don't think there's anything on the Zoom side.
No, you're good. You're good with,
Okay.
with the questions on through Whova. Okay, and I think on that note then, Sean, or did you want to say some closing remarks? And as you talk, we'll see if we have any other questions come in.
Sure, absolutely. So what I'll do is, Andy, I'm just going to ask you to stop sharing your screen.
And I thought everybody wanted to keep staring at my face. Sorry about that.
Yeah, that's all good. Perfect. And really what I'll do is just conclude with the points on our program that we mentioned yesterday. And then I'll give Andy a point to just give a bit more detail on his upcoming courses. And then that'll really be it. So let me just switch views here. Everyone should be able to see that. Really, I introduced this yesterday, the 3 new program streams that we are undertaking with this initiative with McMaster University. And now reaching out to quite a wide range of associations, OSF being one of them as well. So those program streams, again, being the Circular Economy and Climate Change stream, the Advanced Manufacturing Industry 4.0, and then the Industry Operations and Leadership and Management stream. I just wanted to touch base on this. This was really one of the attributes that we were mentioning. So the value being the guest speakers in the program. So I'll really just showcase a few just on top of what Andy was mentioning. So for example, we have Dave here, who was the vice president of Boeing. He just retired as well. He's been really instrumental in shaping the program, connecting us with Boeing Canada as well. But he really speaks to high performance leadership and character development, and really those challenges under very, very turbulent times. And he speaks to the 777 program as well as the 737 MAX issues that were prevalent last year as well. So that was really well received by our participants. We also have Egan and Philippa here. Philippa has been really great. She joined us from East Asia, from Volvo, and really talked to us about the logistics challenges at the time of the pandemic itself. And now this year, she's updated her content, really just showing how they've moved from a lean model to more of an agile model. And now we're looking at the reasons for it, especially from the supply chain issues we're currently facing. So that has been really exciting as well. I always like to mention Nancy and Nicole, both recently recognized as one of the top 100 women in Canada. Nancy in particular has been instrumental in shaping our mentorship program. She instructs the mentorship lesson on the course as well. And then finally, I'll end with Shelley, who joined us from Lockheed Martin, and she leads the augmented and mixed reality initiatives with Lockheed Martin Space. And it's been excellent seeing her insight with regards to 50 to upwards of a 90 2% reduction in cycle time on some assembly operations using the NASA Orion space capsule as the primary testing bed, and then how they're using those lessons learned on the F-35 program itself. So that's been really interesting as well. That's a very small snapshot of the guest speakers and the teams that we usually get to drive the content. This I really just wanted to show. It's from my the Advanced Leadership Skills course, and really just shows the breakdown of the members on the program. So you can see here, we've got members from multiple different departments within industry organizations, both from the large and small medium enterprises, suppliers as well. And this gives you a quick breakdown. This is just from my course, but very, very similar industry domains across all three of our programs. This was one of the continuous improvement activities that we did. This was from my particular course, the Advanced Leadership Skills course, where we asked all the participants to rate each guest speaker in terms of relevance for the content. And this is really the effect that we're being able to drive from the industry first approach. To give you an idea, so yellow is content and value, that they understood both. Green was that they were planning to implement those lessons learned within 3 months of the program. And then blue was that they were already implementing it within the 3 weeks of my program, because my courses are split up over 3 weeks. So we've been very, very happy with the feedback we've been getting and optimizing it after each course. So I spent a bit of time yesterday introducing the courses. And, I talked about the circular economy course, which started everything off, carbon mitigation, but I'll really just touch base on this one and just focus on what's coming up in the fall. So we have our leading transition course, really focused for mid to strategic level leaders and really instructing those lessons learned on how to transition a business unit, adopting attributes of carbon mitigation or circular economy. That's going to kick off in February. And then actually I'll let Andy speak to his 4 courses, which are kicking off in February as well. So Andy, are you still on the call?
Yes, I'm still here. So yeah, if you just want to leave those up, then Sean. So sure. So we've got the four courses or 4 modules there: the Industry 4.0 and CPS, the Advanced Manufacturing and Hybrid, Big Data and Cyber, and the Automation. These all really fit underneath that Advanced Manufacturing and Industry 4.0 umbrella. Of course, with having 4 modules like that, they're all focused. So the first one is a little bit more in line with what we did tonight, or what we discussed tonight. So it's really showing people what is Industry 4.0, what is industrial IoT, how do you deploy it? And as I mentioned earlier, we're going to be showing you how to physically connect things up and get data. And the idea there, again, is, I love this stuff. So I want to show people how quickly it can be done, how quickly it can be deployed, just to start getting your feet wet with the technology. The next module is the Advanced Manufacturing and Hybrid Engineering. And that one, we have a lot of input from some simulation companies and suppliers in the additive space. So in there, we're talking about additive. We talk about the benefits. We don't shy away from the pitfalls of additive. One of the unique things that we do is we lead a workshop where we focus on not only case studies, but we show you how to actually audit your own products to see what is a fit and what is not a fit for an additive process. So one of the things that we did in our first go around is everybody goes away and they come back with a part from their specific operation. Some people can do that, some people cannot, but we show them actually how to audit it. So we start to show them what are the critical features you need to be looking for, whether it's geometry, surface finishes, types of material, setups, pre-processing, post-processing. So we kind of cover all of that in that course to try to get you thinking about additive. And we do bring in simulation as well. So we talk about simulation of processes and operations. If you want to just scroll down there, Sean, to the last 2, big data, AI, and cyber. So in that one, we're really focused on data collection. what does it mean to have big data flowing through your facility. We touch on cyber a little bit, but the main focus is on data collection. How do we manage high throughputs of data? Where do we store it? Do we store it on an edge system? Do we store it in the cloud? Do we store it on servers? And we really work to demystify this idea of machine learning and AI. It's stats. So we try to demystify that. And one of the cool things is we have a couple of people from the bank that come in, because if anybody knows about AI and managing data, the bank certainly have got it all figured out. On the automation side, so we'll have a few automation companies come in and we have them talk about automation. Again, it's not a sales pitch. We do a heavy focus on simulation so that we can really get companies looking at where is their actual value and benefit to automation, or where is their value and benefit to, say, adding new pieces of equipment or new pieces of technology. So it's a very heavy focus, again, on automation technologies and simulation. So I'll stop there.
No, that's great. Thanks, Andy. And really, I'll just wrap it up with what's coming up next. So I already talked a quick second yesterday about the Industry Operations Leadership and Management Program. So you know there's 5 courses within it. This is the one program where we recommend members enroll as a full program participant. Individual courses are absolutely available for each member. The main difference is that we have the group mentorship program, the industry business unit project itself, quarterly networking events. There's a letter of recognition as well that augments a work portfolio. The tools and the continuous learning that I mentioned for post-course access. But really I already covered quite a bit of detail on that with Jamie yesterday, and he being one of the guest speakers in the program. And really what we're looking at is, like Andy mentioned, we use a variety of different platforms, Simulate, OBS as I'm using now, Mural, Tuvuti being the main learning management system itself that we deliver the content. And really, this is the main initiative. So under the AMP Up program, we've been able to subsidize the cost of the programs for OSET members themselves. So you can see it brings the cost down from the 2,000 regular cost plus HST down to 750 Canadian, and it's the exact same for the IOLM program from 10,000 to 3,750. So really, this is what's coming up next for us. The Industry Leadership Program will be kicking off on the 10th of January. So we'll be looking to finalize registration probably by second week of December. We're doing already end of November with the industry clients that are sending their teams. Andy's course, Advanced Manufacturing Industry 4.0 program, will be kicking off around the early February mark there. You can see it'll go till about April. And then finally, we've got in the fall, that Leading Transition course on February 23rd. So over the next few weeks, very excited that we're going to be sharing that information through OSET. You'll see a variety of different communications taking place. But that's really it, and the benefit to OSET members. So on that note, Costas, I'll hand it over to you. If there's any questions or comments in the chat, I'll stay on for another minute or so. Please, by all means, feel free to ask.
Thank you. Thank you very much. Thanks, guys. Thanks for that presentation. Thanks for the input. And as I said yesterday, OSET is looking forward to this new partnership and continuing to bring value to our members and helping them continue their career development activities. On that note, I mean, again, if there's any questions, please feel free to add them to the chat. I will start to kind of wrap some things up here. Just to let everybody know, this was the last CPD session of our virtual conference. Tomorrow is the YPC, the Young Professionals Committee Town Hall, and there's a very interesting keynote presentation by Chris Cook, who is an athlete, adventurer, and farmer. Have a look at the agenda item. I have a movie in there for you guys to see. It's truly something and speaks to the resilience, which is what the theme of the conference is. On that note, I don't see anything else. So won't take up any more of your time. It's almost 8 o'clock now. So thank you very much for joining us. Sean, thank you. Andy, thank you for joining us.
Thank you for having me.
Thank you, definitely.
And I look forward to working with you guys real soon. Have a good night, everybody.
Have a good night, everyone. Thank you.
Have a good one.